हाँ विकास, आर यू देयर? हेलो
यस
विकास।
सर।
अच्छा
यस सर।
ठीक है।
यस सर।
हाँ तो अभी सर ज्वाइन करेंगे उसके देख लेना 4-5 पार्टिसिपेंट हो जाएं और सर ज्वाइन कर दिए हों तो स्टार्ट कर लेना। मैंने रिकॉर्डिंग ऑन कर
यस
दिया है,
सर।
ठीक है ना सर?
यस सर। यस।
तो मैं मीटिंग छोड़ रहा ना।
ठीक, ओके।
हाँ ठीक है।
गुड मॉर्निंग सर।
Hello, good morning, everybody.
Good morning, sir. I, Vikas Kumar, going to give a brief introduction about the expert of today's session,
My voice
Dr.
is
Rajesh.
coming.
Yes, sir. Hello. Hello.
Can anybody confirm if I'm audible?
Yes, sir.
Sir, the voice is audible.
Hello. You hear to me? Hello. Hello. Sorry, you hear to me? Hello. 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 Sir, you hear to me? Anyone confirm me?
Yeah, good morning.
Good morning,
I'm
everyone.
audible. Anybody can confirm?
Yes, sir.
Okay, Mr. Vikas,
Yes, sir. I am audible, sir.
Niganka Mukherjee, Nehal, Vivek Kumar, Vandita Pandey, Devrat Harshvardhan.
I am audible, sir. Hello.
Prabhakar Singh.
Yes, sir, you are audible.
Rajesh Gupta, sir. I am audible.
You are audible because, yeah. Good morning,
Yes.
sir.
Good morning,
Yeah.
everyone. Good morning, everyone. I, Vikas, going to give a brief introduction about the expert of today's sessions, Dr. Rajesh Gupta, sir, who will give a deep insights of AC/DC hybrid microgrid and its control in renewable energy driven distribution system. Dr. Rajesh Gupta, sir, is a professor in a department of electrical
Dr.
engineering.
Saran, if my voice is coming?
Yes, sir.
Yes, sir, your voice is coming, sir. Because you can continue.
Electrical engineering, Motilal Nehru National Institute of Technology, Allahabad, Prayagraj. He received the bachelor's in electrical engineering from the M Engineering College, Gorakhpur in 1993. Master's degree in control system from BIT Mesra, Ranchi in 1995. And the PhD
Dr.
degree in
Saran,
the
can you unmute?
area of
Sir. Yeah, I'm Dr. Arvind Kumar
power
Prajapati, sir.
electronics.
I'm handling his account, sir. Yeah, because you can continue.
Control from the IIT Kanpur in 2007. From 1995 to 1996, he worked in IET Lucknow, and from 1996 to 1999, he worked in GB Pant Engineering College, Pauri, Garhwal. His research interest includes the power electronics, control techniques, solar PV, wind power conversion, grid-scale energy storage, electric vehicles, microgrid, etc. He guided the 14 PhD students and 65
Dr.
master
Saran.
students and published 200 research papers. He was the principal investigator for the research project sponsored by the various ministries, including DST, SERB, CSIR, MNRE, NAMPET. He has been granted 4 patents and 5 won. He also worked with the industrial project and consultancy with the NTPC, Tata Power, CPWD, NCC Limited, etc. Dr. Gupta has served as Vice Chairman and Secretary in the IEEE Uttar Pradesh section and IEEE Joint Chapter of IEPLCS. He is a recipient of 2013 IEEE Outstanding Branch Counselor Award of Region 10 of IEEE. He is also a recipient of 2014 IEEE Outstanding Volunteer Awards of IEEE Uttar Pradesh section. He has a first prize winner of VI Mantra test in 2006 organized by the National Instruments. 2 of his PhD students and 2 master's students has won the POSCO Awards sponsored by the Power Grid Corporation of India in association with IIT Delhi. His name appears in the top 2 scientists in the world under the category of electrical and electronics, published by the Stanford University Constitutively for the year 2022-24. Dr. Gupta is serving as an associate editor of IEEE Transaction on the energy conversion and the IEEE Power and Energy Society letters. Now, without taking much time, I warmly welcome and invite Dr. Gupta sir to deliver his sessions. Over you, sir. Hello.
sir, you can share your screen, sir.
Rajesh Gupta sir.
Sir,
Audio is not reaching to the Rajesh Gupta sir.
sir, can you share your screen, sir?
Sir, audio is not reaching to Rajesh Gupta sir, so he can't answer.
Sir, unmute. Rajesh, sir, you can unmute, sir. You are mute.
At least 3 Indian nationals have died and 5 others remain.
Dr. Prajapati?
Yes, sir. Yes, sir. You are audible, sir.
Acha. So, shall we start?
Yes, sir. Yeah, you can start, sir.
Okay. This PPT is visible?
Sir.
Yes, sir.
Yes. PPT is visible.
Acha. Okay. So, good morning, everybody. Everything is set. Now, I am starting my PPT. Okay.
Yes, sir.
Everything is clear, sir. Start.
Okay. Thank you so much. Okay. So I thank the team of this FDP, especially Dr. Saran and Dr. Prajapati and other members who are coordinators. I thank both the departments of Electrical Engineering, MNNIT, and NIT Patna for arranging this useful session and this useful faculty development program. I congratulate also to all the coordinators, conveners, team members, institutes, and also to the participants who have patiently attending this faculty development program for past few days. And I think this is the last day of your program. So I am in front of you today. So I am Rajesh Gupta. I am professor in the Department of Electrical Engineering, MNNIT Allahabad. And I am presenting today on the topic, as I shared earlier, AC-DC hybrid microgrid and its control in renewable energy driven distribution system. So typically I cover some of the parts, especially database of renewable energy of our country, and then I will be coming to the control aspects when you have renewables as one of the major participant of a microgrid. So, okay, so I'll just first of all put before you some of the things, important or key concepts which is related to grid and microgrid, especially as far as renewables are concerned. So renewable energy targets we have, it was in 2017 around, the government has set up a target of 175 gigawatt, and that time it was fixed to complete or achieve this target by 2022. But due to many reasons, due to COVID especially, this target could not be met out, and later it was extended till 2024. But fortunately now everything is okay, and more than 175 gigawatt has been installed beyond 2025. So basically, development of renewables have led to the development of microgrid also, and also the requirement. Now further, because we are moving towards the era of non-fossil fuels, so government has another target of 500 gigawatt, that is 50% of energy requirement from renewable by 2030. Then there is another major component of storage, because till now we are talking about only renewable energy, grid, and intermittencies of renewables. So another component which is supposed to play a role in a microgrid is a storage. So as if now there are certain storage, but when we are talking about the grid interconnectivity direct, it is actually the battery energy storage. So government has another target of putting 27 gigawatt. That means 27,000 megawatt, and with the again a target of 4 hours backup, and it is projected for till 2030. So this is one of the things which has to go up. Already started the national storage scheme and other things are coming up, and we have to have these storage in our grid system. Then, as all of you know, that there is a global target of achieving net zero carbon emission by 2070. So India need to generate 83% electricity from renewable in order to achieve net zero carbon emission, and our country has set up a target up to 2050. And whenever we talk about net zero carbon emission, it really doesn't mean that we are going to eliminate our fossil fuel generation. It only means that whatever carbon we are emitting from the thermal power stations, especially, it needs to be equally compensated by generation of green energy, so that on a net basis we say that zero carbon has been emitted. Another important projection is that by 2030, about 43% of transportation sector will be from electric vehicles. So somehow these things actually led to the requirement of microgrid. So that's a very important challenge. I will be briefly talking about our installed capacity first of all, and then coming to the microgrid. So energy and the power generation in our country will actually decide the kind of pattern, the development of grid connectivity and DC and AC microgrids, or it's a hybrid microgrid. So this is one of the very recent data I just collected from the website of a Central Electricity Authority, and it's a dynamic data, but it is very good to have the information about this. So as if now, August 2025, just a couple of months back, we have a total thermal installation of 244 gigawatt, which amounts to about 49% of our total installed capacity of 495 gigawatt. So first of all, we are close to 500 gigawatt by this year, or almost achieved 500 gigawatt of total power capacity installation. 50% is still thermal, and it will continue to be there in our system because this is the source which is most reliable and controllable. So control in a grid is actually governed primarily by the thermal power stations, and they will continue to do so. Maybe their percentage will keep on decreasing. If you remember, about 10 years back, the thermal was 70%, now it is 49%. So it's a good thing to have it. Then renewable energy, as I mentioned, we already achieved a target of 175 gigawatt, and now we exceeded this year by another 20 gigawatt, that is totaling about 192 gigawatt, and it amounts about 38% of the total installed power. Hydro, as usual, 50 gigawatt, it is there for a long time. Nuclear 8.8 gigawatt. So this is all our tally as if now, as far as total installed capacity is concerned. Here I would like to emphasize on one point actually. When we say RES, so RES it's actually a renewable energy sources, and it consists of small hydro, biomass, wastewater, solar and wind energy. Okay, so and it is managed by Ministry of New Renewable Energy. Remember that. So it's a data which is MNRE generated data, that we have about 38% of RES. But globally, we recognize that RES and hydro are both renewable, as you all understand also. So when we say on a global front, we combined RES and hydro. And in 2019, our country also now combines both the data, and now we can say we have 242 gigawatt of renewables. So now it's almost 50-50. that we have renewables about 242 gigawatt and thermal about 244 gigawatt. So, and now we are in line with the global data sharing. Now, as far as renewables are concerned, RES, it is totally RES. We don't say renewable. Renewable means RES plus large hydro, like our hydro projects, major. So solar we have now about 123 gigawatt, which is amounting to about 64% of total RES. And wind is 52.6 gigawatt, which is 27%. So a couple of years back, I remember it, both were 40-40. So 50-50% we had from solar and wind, but now solar, as you know, there are a lot of schemes for solar and it exceeded now. Small hydro 5.1 megawatt and bioenergy 11.5. So this is a breakup of our RES. This is our potential for RES especially. We have 750 gigawatt of potential for solar, 300 gigawatt of wind, and bio 25, small hydro 50. So this potential is a is a threshold, we can say. We can achieve or maybe after 50 years or maybe 40 years, something like that. So this is a scenario of renewables and RES, which actually give us a base why to go for smart grid, microgrid, and different control aspects of a RES. So any point if somebody want to interrupt or ask any questions, so you are most welcome. I hope till now I'm okay. The slides are okay, and everything is going fine. Anybody can confirm, or anybody has any kind of questions, so you are most welcome to ask. Okay, so if everything is okay, I should continue. But anybody can interrupt in the middle and can ask the questions. Now, this is a global installed capacity of renewable, and that's what we now talking about globally. What is the status of our renewable energy? So when we talk about globally, always remember renewable is the sum of RES plus bigger hydro. Okay, small hydro is already there in RES, but we till 2019 we separated out bigger hydro projects under the Ministry of Power. It is still under the Ministry of Power, but as far as data is concerned, it is now combined. So if you look upon this, by 2023, this is up to 2023, not of today. This is the older data a little bit. So China is a leading country in terms of renewables, which has 1453 gigawatt, which is far ahead from other countries, especially US, Brazil, and even our country. So we are standing fourth in terms of renewables as if now. So lot more have to go, because in terms of population also, if we can say China and India are compatible, so this indicates that per capita consumption for our country is much less, and also industrialization growth of the China is much higher as compared to our country. So somewhere we have a lot of scope to grow, and already things are going in a positive direction. A lot of industrial revolutions and many Make in India kind of things are coming up, which will actually put our country also at some better stage. So this is the global things about the renewables. Now, as far as renewables concerned and their utilization concerned, we are now at a very matured stage where we can easily transfer our power generated from renewable to the local loads, and also we can actually uh, grid interactivity is possible, uh, and those technologies are now much matured. So, and the issue of microgrid actually starts coming, especially when we want to utilize the renewables in a standalone manner. Else, the grid challenges are different, the microgrid challenges are different. But as a whole, let me summarize some of the challenges which we face when we interact the renewable energy into the grid. So these include power quality. So one by one, one or two line I can talk about. Power quality includes harmonic injection from the inverter based resources, DC injection because of the unbalancing and other failures of the power electronics converters, uh, voltage sag and swell, voltage droop, frequency variations. So these all are part of a power quality aspect when we go with the renewable energy based injection in a grid or microgrid, both. Reliability is another aspect which actually require attention, because as we grow with the renewables, it's a big challenge, reliability, because till now our power systems are very reliable and we have a good resiliency with respect to the faults. Uh, but with time we have to look upon that new challenges, that how reliable is our grid uh, when we move from fossil to non-fossil era. Safety and protection, uh, especially the protection, is a very big challenge now, because we are very good with the AC protection schemes. We have a good circuit breaker, relays and other things which works very well with a quenching and other phenomena, with a zero crossing of the AC. But with the DC development, because of the renewables, especially in solar and solar freight, microgrid and grid, protection is one of the biggest challenge, and we are working on that also, that how to utilize the newer solid state converters for protection of a DC microgrid. So that's a big area ahead, and we need a lot of standardization. Load management, of course, especially in a standalone and microgrids, this is load management is one of the big challenge. Then grid interconnection and control. So if we want to connect our microgrid with a grid, or vice versa, in order to have more energy from the grid and to transfer the energy to the grid, this is one of the challenge. New regulations have to come up as far as development of DC microgrid and hybrid microgrid. We still need standards and the regulatory authority to develop these type of new ways. One of the very important topic of research is a fault right through capability or fault right through requirements. As we all know that our conventional grid is very much resilient to the fault right through. If there is a fault in a system, we have a well matured power plants which can continue to be remain connected in a grid if you have a fault. And this phenomena is called fault right through requirement or capability. So, but with the development of renewables, especially solar, wind still have some resiliency towards the fault right through, but solar is zero resilient to the fault right through, and that is one of the bigger challenge. And we have to find out the ways to actually solve this problem. There are a lot of solar projects which are still lying ready, but they cannot be interfaced to the grid because of this problem. And lot has to be done. Then grid operation economy is one of the important thing, because till now we have a conventional sources and their operations are throughout uniform, but now with the development of renewables, price variation is lot actually. So this is one of the again area which needs which is continuously evolving. How to find out the dynamic pricing, how to find out the load dispatch based on which source to connect in a system and which not to connect. Another challenges which include voltage varying and instantaneous active and reactive power control, and islanded is one of the challenge of a microgrid. Okay, so we have a paradigm shift in the operation of a grid. Classical dispatch, which we till now have, that we forecast the load and generation has to follow the load. That's what our conventional, or we call it as a classical dispatch. But renewable generation dispatch, which we call a new era, where we not only forecast the renewable energy, but also forecast the load. Not only forecast the load, but we also forecast the renewable energy. And that gives us a net load. That is load minus renewable energy. And now the generator has to follow the net load. So because now the two things is the unreliable. One, the load, which is totally independent, and renewable energy, because this is intermittent. So we don't know what will happen tomorrow about the renewable. So we have to forecast. There has to be a forecast mechanism which not only forecasts the load but also the renewable. And then we have to decide how to transfer our conventional power. So storage has to play a vital role in this case to negate the intermittency, and a flexible power system is what required, that we call also as smart grid. So just two examples how solar and wind can be intermittent. So you can see one of the profile of a solar with a 24-hour span on the x-axis. Of course, till morning you don't have any solar energy, and it start growing with early morning and then finally reaches to peak towards the midday. But even when you reach to the peak, it is highly oscillating. It may go up and down and then finally go down. So although we have good profiles of the solar, but in one of the worst case scenario could be like this. Okay, and and it's any place data. It's nothing like this is a location is specific, because across the year, uh, someday you will definitely have this type of profile. Wind speed, as far as wind speed is concerned, you can have another data, like how the wind is changing and how its profile will keep on changing with time, with months, and that too is highly intermittent. So the point is that how much can we rely, and what the technology has to support in order to mitigate these intermittency. So one of the solution for this compensation of intermittency is the storage, and that's what I mentioned in the beginning also, that we need a storage to actually interface with the grid, so that during the time of variations we can actually. So till now we have a very small 2500 gigawatt hour storage in the grid, which include pumped hydro storage also. So we have to go long way in parallel with the renewable energy development in order to have a good balance of renewable and the load. Otherwise, it will be a kind of a imbalance situation, and there could be a fallout of the grid, or some other things can happen. So, as I already mentioned, that we have a lot of targets for storage also, but some of the things have to go like this. This is the way we can consider any grid connectivity, renewables, and storage also, and where the storage can play a role. That's what is all visible in this plot. In AC grid, if this is a conventional thermal power plants, we have some backup storage for other purposes, not for supporting the energy, but for some auxiliary supply and other requirements. We have storage in very high loads, high voltage loads, to maintain the voltage regulation and other things. Then we have in distribution levels, you can see these are the distribution level. We have to keep a storage in such cases to levelize the or peak shaving the load. So fortunately, renewables are available during peak period. So that kind of balance we can make. Then we have a renewable supply as a centralized supply station. So there we need a storage for generation leveling, congestion relief. So a lot of roles storage plays in a both in a transmission, generation, and distribution. So as far as our power system is concerned, you see we have generation, transmission, and distribution, and in future the storage can be a part of all these three power system subdomains. So focused on microgrid. What is basically a microgrid? It is actually a low voltage distribution system with distributed energy resources like PV, wind, fuel cell, together with storage. That is flywheel, batteries, even energy capacitors like supercapacitors or normal capacitors, and a controllable load. So here the load is termed controllable because it may not be necessary to supply the load at a same voltage all the time. So based on the load frequency control in case of AC microgrid and voltage droop control in case of DC microgrid, the loads we also call it as a controllable. So these systems are interconnected to the medium voltage distribution system, but may also be operated isolated from the GIS in case of fault in upstream network. So idea is that a microgrid is a combination of a distributed resources, storage, and controllable loads, and it can be connected to its mega grid, means grid, or it can be isolated. It depends upon the application. It depends upon the size of the system, reliability requirement in a system. Then what type of decision we make regarding the control, centralized or distributed, or other methods of control of a microgrid, that we'll briefly discuss. Then power flow can be bidirectional. In microgrid, power flow can be bidirectional because we have a storage. So that's what the little brief about the microgrid. Microgrid again in a different graphical view. It's a normal mega grid, means our grid, and then this is the microgrid, and then we have a microgrid consisting of storage and flexible distributed generation, and smart network and demand response is a part of a mega grid. So this is a view, graphical view. We see about the microgrid representation. Now, a little bit more brief about the microgrid graphically. So you can see some of the things which will give you more insight into the microgrid. So this is say a microgrid. So you can see these are the loads. These are some of the transformers which are connected to the at different voltage levels. It will be used at a different voltage levels. Then we have our distributed resources. You can see here distributed resources. Then communication from the sensors and actuators in a microgrid, and then there is a power grid, and that's how we can represent it over here. A good pictorial representation. What are the features? Remote area electrification through renewables. This is what we say. Remote area, we can go with a microgrid if we don't have a regular grid. Deferment of investment in bulk transmission and distribution network. So we quickly need to develop some village or some new places. So we now quickly jump on to the microgrid before we actually think about any grid to reach there. There are some of the countries which are now at 100% renewable, so they are well managing their grids, like Maldives, Bhutan. They are 100% on renewables. Nepal, in some sort. So challenges are there. We can also develop some of the things in our cities and states. Okay, this definitely improves energy efficiency because we are generating and delivering without needing a long transmission networks. Reduces the energy network losses. Support the grid also. It can support the grid. Improves reliability, saves from mass outages or blackout. This is another important point because, as we all know, our regular AC grid is all interconnected. One nation, one grid. That's the concept. But if blackout happens or outages happens, then everything goes down. That time, our microgrid could be a savior. It will be there in system, right? So those are the features. Again, same thing. What are the resources? Distributed resources, energy storage, AC/DC loads. Okay, interlinking and interfacing converters. Okay, so microgrid are classified. There are three major classification of microgrid. One is AC microgrid, DC microgrid, so AC microgrid, DC microgrid, and hybrid AC-DC microgrid. So depending upon the way we are connecting AC buses to the AC load, DC buses to the AC load, or it is a combination of both AC DC loads, so we need a hybrid. So that's how we can understand uh, power electronics has to play and is playing, not only has to play, but is playing a major role in all these scenarios. You see, right now, if you have a PV generation, everything is controlled by PV inverters and so many other power electronics converters. Wind, you know, it's a rectifier inverter based system. Micro turbines, fuel cell, it all largely depends upon resources. As far as resources are concerned, they are all managed by the power electronics. So single bus, so many resources or distributed resources has to come on the same plane with the help of power electronics converter. Now coming to the grid, a microgrid has to interface with the regular grid only through power electronics control. Then storage, bidirectional power flow is only possible with the power electronics converter, whether isolated or non-isolated converters. And then driving your AC load or a DC load, because you know, especially if you look upon DC loads, we have now a DC loads right from 5 volt up to 300 volt. DC loads are there. So you need converters which can bring down your DC bus voltage into a different LVDC, we call low voltage distribution system, and MVDC, medium voltage distribution. Okay, so this is some better view of the same thing, how renewables and power electronics can go side by side. This is an example of two generators. One is this is DFIG, which requires doubly fed generators, especially the converters are placed on a rotor side converter. SCIG, squirrel cage induction generator, where the converters are placed on the stator side. And then we have a PMSG, regular PMSG, which is mainly used for high power generations and gearless operation because of the low losses. So we have all the converters in a stator path to deliver a reliable and less losses. Our solar, you see the solar, you have two stages normally, DC-DC for MPPT and DC to AC for AC power conversion. Then a lot of commercial loads, residential loads, industrial loads, they are connected to a bus, our 11 kV bus, which through a transformer supplies the load. Regular grid, let's say 11 kV bus directly connected to the grid, and then the storage, how the storage can be controlled. So a bidirectional converter, which actually transfers the power in both the directions as per the need of and control requirements of the bus. So that's how microgrid can work. Okay. This is a view of two type of grids. One is AC microgrid and another is DC microgrid. So primarily you can see if we have a regular grid, so regular grid will always be AC. We cannot have a DC grid. Okay, it is only DC microgrid which we can talk about. We can't talk about DC grids. Okay, so we have a transformer. In both the cases, we have a transformer. And for AC grid, transformer can feed to a AC bus, We have a different feeders. You can see directly on the transformer, we have a feeders. And then other distributed resources can be interfaced to this AC grid through a suitable DC to AC converter, as we have seen in a previous slide. Batteries will be connected to the AC grid, and through a DC to AC converter or a bidirectional converter, this could be a bidirectional converter, this one. The PV module should be connected to the AC grid through a unidirectional converter, because PV cannot take power. And then there could be a high voltage buses which can directly feed to the loads. Whereas in DC microgrid, you have a regular AC grid, but then you have to have a first AC to DC converter, because the bus we call about is a DC bus. So everything to be connected on DC bus need a conversion into DC, whether from uh, wind, which is AC, to it requires AC to DC, photovoltaic PV modules, DC to DC, batteries, DC to DC, and then we have a load also, which is DC, so DC to DC, and then if you have a AC load, then DC to AC. So that's how we can differentiate between the AC microgrid and DC microgrid. So both have a different challenges. So if we have a AC microgrid, it has their own control scenarios. If we have a DC microgrid, it has its own control scenarios and control requirement. Okay. So let's see some of the things coming to the hybrid AC-DC microgrid. Now, after AC and DC microgrid, we have a hybrid AC-DC microgrid. So, okay, so this is a kind of a structure we can follow for a grid connected system. So you have a point of common coupling here. You can see two buses, one AC bus and another DC bus, right? So both are being fed from AC and DC. You can see it is directly connected to bus, and the other one is connected to the DC through the DC bus. Okay, so that's what you can see here, the differences. AC microgrid configuration. So AC microgrid configuration involve integration of DERs, distributed energy resources, in AC microgrid. Could be done either in single or three-phase, depending upon consumer load premises, connection, or control authority regulations. Okay. And other aspects which are running here, power coordination and control of single and three-phase converters and distributed energy resources, integrated to AC are trending. The current research literature focuses on the following issues in grid connected and islanded mode of operation of the microgrid. It involves voltage sags well in each phase, grid voltage unbalance, reactive power requirement, and active power curtailment. So these are some of the issues which are there in grid connected and islanding mode of operation. So just to give you some idea about the islanding mode of operation. So it is basically a condition of a microgrid when it has to totally detach itself to the main grid because of the fault or any other condition. So whenever there is a grid in a microgrid, when a microgrid is connected to the grid, then there is a support of the grid in terms of control of a microgrid also. So a grid is kind of an infinite bus which can absorb any amount of power, which can deliver any amount of power. So act as a self-balancing mode. The system can work in a self-balancing mode. But the moment you remove the grid, the microgrid becomes like a unsupported, and it has to involve its own mechanism to control. So that is why we have challenges in islanded conditions, uh, which involves voltage Maxwell grid, reactive power, active power curtailment, etc. These are the ways we can actually address the control phenomena in AC microgrid. This is one of the picture I can show, uh, which is actually AC microgrid. Of course, it is a AC microgrid, and you can see that these are the different distributed resources like solar. You can see the solar. Okay, you can see there could be other resources like wind also, which is not visible here, but it can be, and everything is coming to here in a four three phase line. Okay, and then we have a regular grid, uh, which is also there. Regular grid is also there. You can see here. So many things are there, and we need to how we need to manage. Even we can have a DC microgrid or DC grid also. So three interlinking converter, we can connect different AC and DC grids together through an interlinking converter. You can see here. This is a kind of a distributed, decentralized or decentralized distributed energy system. This is centralized where we have one control over a large uh, voltage bus, and here we have a distributed control. A distributed control at a low voltage bus. So it could be your home control. A solar connected in your home in part of a microgrid is a distributed control. So that's working very fine these days, and is supposed to play a vital role in a coming year when we have islanded DC microgrid. So that's the kind of scenario we can look upon from the decentralized point of view, that we have a three phases, and then three phases each one is distributed among one another. Now we can talk little bit about the DC microgrid. So DC microgrid could look like this. If I say a single phase DC microgrid, this could be a scenario. You have a solar plant with through DC-DC converter. You have a bus, common bus, where a solar plant and uh, uh, your bidirectional converter can be there. So this bus can be act as a DC bus, and then if you have AC loads, you can connect the AC loads through the another inverter. So that's the kind of a scenario possible. Now, one of the important things which we have to, as far as control is concerned, we call it as a droop control characteristic, which is required in a DC microgrid, because it is kind of a floating system. DC microgrid is kind of a floating system. So the voltage at the bus, PCC bus, need to be controlled in order to maintain the power balance. So this is a DC link capacitor voltage loop control, and this is a power balance loop. So both we have to look upon in order to make a control. Uh, uh, this is a hybrid AC-DC microgrid configuration where we can have two classification. One is coupled hybrid microgrid, another is decoupled hybrid microgrid AC configuration. So couples are normally isolated, and we have a partially isolated, fully isolated, then 2 stage, 3 stage, 1 stage. So different possibilities are also there. Now, in general, as far as control of microgrid is concerned, we have three classes. One is uh, three hierarchical steps, we can say. It's not three classes, three hierarchies there. This is primary control, secondary control, and tertiary control. Okay, so we have whenever we have a microgrid control, so you can classify them in three parts: primary, secondary, and tertiary. So primary control is basically responsible for inner controls, which is exactly at the power electronics converter, like current control, voltage control, right? And it depends upon PQ control, frequency voltage control, like in a drives, like in a other motor-driven applications. Basically, to maintain the performance in the uh, AC load side. Then secondary control acts as a centralized automatic generation controller and checks steady state errors in microgrid voltage and frequency using communication system. So secondary control is assisted with a communication system to have next level control, especially bigger DC bus voltage control. If it is a AC microgrid, then frequency control. And tertiary is the almost outer level where it is governed by the optimization, economics, and other uh, outside world interaction. Who is doing what, whether to switch to islanded mode, whether to switch to grid connected mode. So that's the tertiary level, right? And this is the hierarchical way: primary, then secondary, and then tertiary. Primary, you can see protection, power sharing, voltage frequency. Uh, Secondary, droop control, active, reactive, grid synchronization. And tertiary, market participation, interconnection, coordination of multiple microgrid, optimization. So these are the various levels, and it is hierarchy. Pictorially, you can see like this, the three levels of control. So you can see almost at the you can see at the load end you have this primary control. This is primary control, which is all doing. You can see frequency, voltage, PQ, and other things. And this is the DER, distributed energy resources. Now, secondary control goes like this. You have some major references of power, reactive power, frequency, voltage, in order to have a droop control or some other frequency voltage control. And then finally, the tertiary, where you have market and other constraint, especially like load dispatch center is giving some signals, or it's a cost effective thing whether to use a grid or not to use a grid, or what type of thing. So this is all the control aspects we can talk about in a microgrid. So control of power converters in a microgrid, especially those who are from power electronic side, we have a grid forming inverters or converter. We call it as a grid forming inverter, which is actually islanded mode of operation. So the converter has to both control the voltage and frequency in this mode of operation, and the power generation and load has to be balanced, because this is islanded. You cannot transfer the excess power to somewhere else. Everything has to be consumed and generated within the closed scenario. So such converters, the inverters we can say, is called grid forming inverters. Okay. Another is a grid feeding inverter, means Your requirement is to feed the uh, grid power into the microgrid, or microgrid power to the grid. So that kind of power balance, or we can't say power balance, but transfer of power from one side to other side, depending upon the requirement and other things. So that's called grid feeding inverters. Okay. It can involve the reactive and real powers. Okay. So frequency is governed by the grid frequency. In grid forming, frequency is decided by the stability point of view. Whereas in grid feeding mode, the frequency is decided by the grid only. So we normally use phase lock loop in grid feeding inverters. Okay, so we can't touch the frequency of a grid. Only thing what we can do, we can change the active and reactive power and which side it has to go. That's a grid feeding mode or grid feeding inverters. Grid supporting or weak grid support power converters are like you are using inverters for the purpose of support, like you are using a STATCOM, D-STATCOM, okay, DVR, this type of scenario where maybe these are supported by the renewable energy, but it is connected to the main grid, not for the purpose of directly transferring the power to the grid, but for supporting the grids to improve the power factor, to improve the harmonic distortion, and such type of scenarios. Okay. So beyond microgrid, we basically have a smart grid which has to play. It involves power and intelligence, IT and communication to have a smart grid. So a smart grid is an amalgamation of electrical infrastructure, information and communication technology. Now some of the examples I will put forward to you, which we have done as a part of a project of some government agencies and others, where these things are involved, like microgrid, AC, DC, and other applications. So you can see a typical microgrid application, standalone and grid connected mode. Here you can see this is one of the project I guess we have done with MNRE, Ministry of New Renewable Energy. We developed this the experimental setups in our lab. So we have a solar which is driven through a DC-DC converter to a DC microgrid which is 340 volt. So 340 volt DC microgrid we created, and that is supported by a bidirectional converter. We had a battery, we had a supercapacitor also in this mode, so as to support a 340 volt DC-DC converter. Now this 340 volt DC-DC converter, we have a control mechanism which we have done it for with the help of a sliding mode control, and through an inverter which is feeding to the main AC grid, 230 volt single phase. So this was a small, you can say, lab level microgrid where we created 340 volt DC with the help of renewables, and single phase AC we have taken, and this is the grid following inverter single phase which is used for transferring power from the DC microgrid to grid or grid to DC microgrid. This is the extended version of the same project where we have used solar, wind, and AC as well. And then we have two buses. 380 volt is a regular bus for DC microgrid. Then we have a low voltage LVDC. We call this as MVDC, 380 volt MVDC, and 24 or 48 volt as a LVDC bus. So on LVDC bus, we put up a batteries, buck converter, and our local DC loads, where power balance can be managed. And on the here we have a control between solar and wind in order to balance the voltage. So sometimes one of the challenge which we have seen with this system, is to extraction of maximum power. So normally we operated solar at a maximum power, and then DC, this wind is operated at a suboptimal point, we can say, or vice versa. It depends upon the scenarios, because you need to maintain a constant voltage over here. Then we have a AC grid also, which we have a energy management system through which you have a AC loads as well. So we have a low power DC loads, 24 or 48 volt, and we have a regular three-phase AC load or single-phase AC load here. So this was a part of a same MNRE project we have done with a hybrid DC AC microgrid. This is the detailed structure, how we did it in a lab. This is a regular three-phase grid, how we interconnected with this 380 volt DC bus, which we called MVDC, and this is LVDC, MVDC loads, LVDC loads, and then we have a bidirectional converter, non-isolated, and then we have interlinking connected with AC and DC. This is storage we used through a bidirectional DC-DC converter. Another battery stack. Sorry, this is a ultra capacitor. We put up a super capacitor, ultra capacitor in a DC bus for temporary support of the DC bus, especially during the transient period. And then we have a regular batteries which is used for the support of a MVDC in case of no solar, no wind, no both, or we don't want to operate great, and or during blackout, batteries of much use in those conditions. So this is how we worked on this system. These are some of the parameters which we have used in laboratory scale DC microgrid, DC AC microgrid, hybrid you can say. So detailed data is available. These are some of the results which we generated under different solar scenario, under different state of charge of the battery, under different load scenarios. So many results we generated. Basically, how to maintain reactive and how to support reactive power in order to balance the real power, and with a different variation in a load scenario. And this is what the DC, MVDC and LVDC is working. You can see this is the result for MVDC, how we are managing the voltage. Some of other results. So results are all part of a things which you can extract from, and all the papers are available. In case somebody is very much interested, they can look upon papers on these topics for detailed understanding. Three modes basically. One is active grid interconnection mode, passive grid interconnection, partially grid connected, and this is totally islanded mode. So this was one of the big challenge when we did it, because in grid connected mode we basically used a current control mode of operation, and when we shifted to the islanded mode, we have to shift our control to the voltage mode of control. So that was one of the things which we faced the problem while implementation in a hardware, okay, an experimental setup, because changeover required a detection and other aspects. But yeah, did it in some better way. And again, different SOC levels of the battery, how we manage the power balance, that's another challenge. And sometime we have to use dumping loads also in order to waste the power. Suppose you are on a no load situation and renewables are there, and so what to do? So we basically use the dumping loads in those scenarios. Although there are other ways around also, but a lot of possibilities are there. This is another very small example we did, like a solar and battery with a load. So it's like a totally a DC microgrid situation. A solar plant and a battery energy storage and a DC load. So how we can make a power balance using droop voltage control. Okay. These are some of the ratings which we have used for purpose of simulation and experimental platforms. Some of the results, how the batteries will charge and discharge if you have only single source like PV. So very simple example, but then ultimately you have to use a control suitable and single converter. So single converter for, two converters for single bus. So there has to be a well-managed control for the two. Okay, so this was some discussion on the microgrid and the related scenarios I have done. Small discussion on the role of solid-state transformer. It's coming up in a microgrid situation as well, and in a regular grid also. So because it is a two grid connection which might be at a different frequencies. So how a solid state transformer can be utilized, especially when you have a grid following case or interlinking converter also, it could be a case. Okay. So a normal transformer, you can say AC to AC, two grid. Then we can have a two-stage converter can be involved, and then we have a three-stage converter where we have AC to DC, then DC to DC, and then DC to AC. So in order to have a transformer like properties that what are the two properties of a transformer? It can step up or step down, and also it provides isolation. So solid state transformer can be used to serve these two purposes. But it normally involves three stages. One AC to DC, then DC to DC with isolation. Normally we can represent it with by a dual active bridge, and then DC to AC to connect another grid. So one of the side of these system could be a microgrid. So in a typical AC microgrid, grid connected, you can have this type of arrangement. One side AC microgrid, other side AC regular grid, and then interconnection between the two can be followed through this. Okay. So very emerging topic which could be useful for especially for AC microgrid. It could be useful for DC microgrid also. It could be useful if you use a unidirectional converter on the other side. So that is also possible. Or if you can just remove this stage. So if you make it as a two-stage AC to DC and then DC to DC, and then here you have a DC microgrid. So this arrangement can be a possibility for both AC microgrid as well as the DC microgrid situations. So very emerging, I would say, because most of the energy storage elements like batteries, bigger batteries, battery storage we talked will ultimately be interfaced like this only in a coming grid scenarios. Now for something more detail, you can see the what I was explaining is all visible here. You have a three-phase regular AC grid, and then you have a dual active bridge. You can see first AC to DC conversion, right? And then dual active bridge. Now DC bus of this dual active bridge will be a DC microgrid. Will actually be a DC microgrid. Okay, you can connect your DC loads here, and it could be at a voltage level decided by you only, or as per the requirement of this DC bus. Like it could be 48-volt bus. In a scenario of EV charging, small EV charging, it could be a 48-volt DC bus where you can connect your chargers, DC chargers. And on the other side of this DC bus, you have another 3 to DC to AC converter, and you have a AC bus. So in AC bus, regular AC bus, you have a different type of loads. So a lot of possibilities. If it is a AC microgrid, this side, this is the AC microgrid. On the same AC bus, you have a AC loads. You have a AC distributed resources like solar PV plants, and you can have a DC loads connected on this bus. Okay, so a good arrangement to follow for hybrid AC-DC microgrid. You can see. So see the system, how you are with a fully power electronics controlled uh, and isolated with separate control involved on both AC and DC sides. So this is the symbolically representation: AC grid, solid state transformer, AC microgrid, and a DC microgrid. So this is another emerging topic, that SST in microgrid, solid state transformer in a microgrid. So all the things are very much intercorrelated, but some of the important things are there. So you can see the example which we have again done in one of the project, this thing, that you have a 11 kV distribution system, then we have a bidirectional DC to AC converter, which we call as an interfacing converter. It's connected through a parallel connected DUAV. This is one of the topology we developed from our side, and we have patented this topology also. We have been granted a patent on this topology, that we have multiple primaries which are connected in series, and we have parallel connected secondaries. Okay, so, and why we are doing it? Because this uh, topology, that is the proposed, we call as a multiple parallel connected dual active bridge converter. Uh, if it is power level is very high, that's a big question, that how a single bridge can handle such a large amount of power. So anything which is more than 100 kilowatt or so, we have to use a parallel connected topology. So one way is that simply you connect all the DAV in parallel, both primary and secondary, but that has certain limitations. And what we developed is a series parallel connection. So all the primary on series and all the secondaries are in parallel. And this has some good advantages, especially with a power quality aspect. It has a lot, it has a good cancellation of the ripples and other things. And finally, through a bidirectional DC to AC converter, we have you can see AC microgrid, and from this bus we have a DC microgrid. So this is a detailed structure which I have just explained in this slide. So how a DC microgrid and AC microgrid, and with the power electronics converters, how the AC microgrid and DC microgrid can be connected with a choice of converters also mentioned here. Okay. So I hope this slide will be useful. Most of the topologies which I am presenting here have a supporting publication, and if anybody is interested uh, in any of the topology, you can look upon suitable paper. It's available, or you can contact me also. I can share the link of those papers. Uh, This is the normal futuristic glimpse of a. Yeah. Please. बताएं, आप कुछ बोलना चाह रहे थे? Yeah. Any question or any queries anybody has? Okay, let me. हाँ बताइए.
Hello.
हाँ.
Yeah. What I understand that the load in power system is actually will be random. Means there will be always some stochastic component, but
Yeah.
you can control some of the load, but most of the things is almost it's stochastic nature. Means you can put some sensor or some control, but those are actually in regulatory state. So what do you mean by controllable load?
Okay. Oh, you asked the question in one of the. No, actually, controllable load is only, we can say, in some aspect of uh, this islanded condition. When we have a islanded condition without the support of any grid. So in such situation, we can talk about the controllable load, that we can cut down some non-priority loads in order to make a good balance of distributed resources and a load. So controllable in that sense, not in a sense that we are changing the power requirement of a load. You are right. In most of the, stochastic load and other things which you are saying actually is more valid towards the regular grid connectivity, where we have infinite bus situation and you have a load distributed across the globe or across the country. Right. So definitely no load is controllable. Everybody is free to operate. But in islanded situation, it's a very closed scenario situation. You have to have certain check and balance. Right. So that's the meaning of controllable load. You can say, okay, because in night time you don't have a solar, and in our country we don't even have a wind. So how can you supply a bulk amount of power during the evening or night time? So you have to make some control on the loads. Okay, you don't use your regular heavy loads. You just use your light and fans in the evening. That's the meaning of a controllable load. Nothing more than that. Otherwise, always you can have a. For example, I can give you a very simple example. We are doing it in our lab these days also. That if you have a scenario of, suppose, charging infrastructure from solar PV, okay, and you have a small battery support for storage purpose, correct? So what we can do in this scenario, which is a very good example of a controllable load, I have to charge the electric vehicle battery. So based on the availability of solar power, can we adjust the charging rate of an EV battery? And it is possible. I can make a fast charging. I can make it a medium charging. I can make it a slow charging. Battery is charging, but this is a condition of a islanded operation. I don't have a regular grid support. So that's what I mean by a controllable load. And this we are working also. This particular last example which we have said, that based on the availability of the solar, is it possible that I can change the charging rate of a EV battery? So it's a controllable load. I hope I could convey answer to your question. But in
Yes.
conventional scenario, you are right. Load is stochastic, and if you are a power system student, then definitely the things are dealt in a larger domain. We don't pinpoint these small things. But if you go to the distributed control scenario, these things will come up. And it becomes like a regular things. It's not like it will harm me, right? Within the constraints, I can call or I can regulate the loads also. Okay. Absolutely, this is a very primary level control, I would say, not a tertiary level control or any other thing. Okay, so that's a good clarification, I guess, and I almost finished. So thank you very
Sir,
much.
another.
Yeah, please go
Hello.
ahead. Yeah.
Yeah, I have another doubt regarding the DAB. You are having a transformer in DAB, but it's a transformer less. You are claiming that it's a transformer. What you have claimed? It's a transformer less.
I think you are talking about this transformer. Yeah. This transformer
Yeah,
or this transformer.
yeah. You have the DC and the AC, and from the you have basically in between you have between the AC and AC system you have the DC buffer.
Yeah, these are the DC buffers, and
Yeah.
this is a transformer. Basically, you are
Yeah.
saying about this. So
Yes.
your question is that can't we eliminate the transformer? That's what
Yeah,
is
yeah,
your question.
yeah. That is my exactly the question.
Okay, okay, okay. So why we are calling it as a transformer? First of all, anything which is called transformer must have two properties. One, it has a capability to step down and step up. Second, it must have isolation. Now, in power circuit, okay, isolation when we talk about in a control circuit, there are two type of isolation. One is magnetic and another is optical. But as far as power circuit is there, isolation can only be achieved with the help of a magnetics. And magnetics is only achievable through a two winding transformer. So a transformer, whether it is solid state transformer, whether it is conventional transformer, must have isolation, and isolation can only be achieved with the help of a transformer only. Now, to clarify you better way, in a conventional transformer, our transformer is actually a low frequency transformer. That is a 50 hertz transformer. Okay, and in this, you can, I guess you have a something query in your mind. If I am using a transformer, then why I am using a SST at all? Why there is a three stages? This is a very genuine query, right? But the difference is that this transformer, which you are seeing here in this block diagram, is actually a high frequency transformer. And because it is a high frequency transformer, the size of this transformer could be like 1/10 or 1/100th of the regular transformer. Okay, for example, if I am using a 1 MVA system, if I am using a 1 MVA system, I hope most of you have seen a 1 MVA transformer. I have a substation 33 by 11 kV and I have connected a 1 MVA transformer, right? Most of you know what is the size of 1 MVA transformer. Okay, it may be in several tons, 10 ton or 20 ton, and you need a big cranes and transportation mechanism to install or uninstall it, even to repair it, and to maintain also. Now, how this structure? Now, think about the size of this transformer. This could be like a 10 kg, maybe 100 kg for a 1 MVA system. So I can reduce the size of a transformer from a scale of 100. Okay. So if I'm calling it as a transformer, whether solid state transformer, I must have a transformer. Only thing, I shifted from my low frequency 50 hertz to high frequency 40 kilohertz or 65 kilohertz. It depends upon what the converter switches are operated. So this is purely a power electronics concept that uh, I have decoupled the AC 50 hertz AC with the 40 kilohertz AC with the help of these converters, and therefore I am using a very small transformer which is within a box size, let's say, and that's what the advantage of using a solid state transformer. I hope this is what you had a query, and there are a lot of control methods also which involved in this solid state transformer, and
Yeah.
yeah,
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 that's okay. Yeah, that's a high frequency transformer, and you can go up to say 40 kilohertz or based on your converter switches.
yeah. It depends upon what is your capability of the switches. Higher the frequency, smaller is the size of your transformer. It's
Okay.
that simple.
Can we make the system like this? We have only the DC buffer in between two AC system. Then it's a DC kind of isolation. Then actually there is no electrical isolation for that. But can you tell that that is also a kind of transformer?
Okay, we normally call. Let me better give you example actually. In most of the high power DC EV battery charging, in a high power EV battery charging, like you have a bus battery charging, tractor bus charging, we have this type of structure where on one side, on this side, we have a fully controllable AC to DC converter, and on other side, yeah, this way. This is a better picture to explain the concept. You have, this is a full bridge converter which is fully controllable, and on this side I have a diode bridge rectifier. So what we do actually, the power is only possible to transfer from one side to other side. And if I have a DC microgrid here, so it is possible that I can transfer a power from AC to DC, and that I DC call a DC microgrid. So this is all possible. It is all possible. But the question you asked me is whether I can use is it compulsory to use a transformer in between? So the answer is that normally we use in such cases a high frequency transformer to better isolate DC and AC side, to better have a better protection, and even to have a better voltage level conversion, because transformer is one device which can easily change your voltage. Let's say you have a 300 volt this side, 400 volt this side, and you have a suppose 48 volt this side to charge a battery. Now, if you don't use a transformer, you are right. I can use AC to DC conversion, and then, sorry, DC to AC conversion, and then DC to DC conversion. But then DC to DC converter has to be the part of a 400 volt to 48 volt. I mean, 10 times reduction in a voltage. And if you use this type of converter, the efficiency will fall down very drastically. And in this place, a transformer play a very vital role. It step down the voltage with a very good efficiency of 95% with a high frequency transformer. So that's what the answer I can give you in detail. What the query you have in your mind. It is possible what you are saying, but then it depends upon what is the voltage ratio on the two sides. If you are well managed within the control range of the two converters, rather one converter only, then it is possible. It is possible that you can have a without transformer, but then you must have some other way of around isolation, like solar power is transferring to the some battery. So solar is isolated, battery is isolated. So the two isolated, I don't need any other isolation. Then it is okay. Or passive load, because normally in active loads, two sides transformer is preferable. I hope something inside, but it's again debatable. You can have a lot of other topologies also, which can do these type of jobs. I'm not saying that isolation is must. The bidirectional DC-DC converters are there, which are very commonly used in these applications, which is non-isolated. But it is limited to low power applications. Okay, so non-isolated, you better use for a low power. But as far as medium to high power, we need isolation. And isolation in power circuit can only be provided through any transformer, whether low frequency or in this case a high frequency. I hope my views are clear.
Does any participant have any questions?
Sir, I have another doubt in mind.
Yeah, sure. Please go ahead.
You have mentioned, I think, GFM and GFL, both the converters, and you have mentioned some other thing regarding the weak grid. Can you?
Yeah, actually, it's like we have a conventional, uh, I mean, I can just quote example, a solar fed distribution system where the role of solar is to compensate the harmonics, let's say. This is the role of solar. I mean, it's not primary role of solar, but it is something like that. In a distribution system, you have loads which are non-linear, so it draws a lot of harmonics. So what I can do, I can in place of any passive filter, I can put a active power filter. Let's say active power filter, which is nothing but an inverter, and on the DC side I have a solar, and on the AC side I have a my non-linear load, and which is actually regularly fed from the AC distribution system. So this is like a shunt active compensation, right? Now in this scenario, a solar is a energy source, okay, which can transfer the power into the grid to feed to the load. Additionally, the inverter can act like a active power filter, shunt active power filter, to sync the nonlinear loads of the nonlinear load harmonics. Therefore, the regular grid can see this as a linear, and therefore the inverter is behaving like a compensator as well as the energy source. So such type of applications can be categorized under the this third category which you mentioned. And a lot of examples are there for this.
Okay, it's
So
basically
earlier, a decade back, this
it's a basically
yeah,
active.
please.
You
Yeah,
have,
it is one only. Active power filter is one example.
okay.
You can have a series compensator also, not a problem, like a dynamic voltage restorer, which is very well need energy support. Even active power filter can be energy free. It can support it from the DC capacitor. That is there. But if you go for a series compensation like a dynamic voltage restorer, it definitely requires some energy support. So there are examples that solar is there, and it is compensating the sag and swell from the grid side for maintaining a critical load voltage constant. This is very common example. But nowadays, in terms of this grid feeding, grid following, this is one of another example which are not in both the categories, but it can be categorized third. So anything else can be categorized in this third, which is doing the dual support. So weak grid has these type of problems in distribution system, that sags well, and because our normal loads are directly connected in a weak grid. So many times we can use inverters to support these power quality problems, and we can have this type of inverters of use. Okay, it was a good question and
Are there any
scenario.
questions?
Anybody else, if you have anything in your mind other than this also, we can have few minutes to answer a couple
Are
of.
there any questions? Please ask. There is no questions. Thank you so much, sir.
Thank you. Thank you, Dr.
For your insightful and engaging sessions. Your valuable thoughts and examples are truly enriched our understanding of these topics. Thank you so much, sir.
Thank you, and thank you all the participants. If you have any further query, you can connect to me, you can mail to me. I am more than happy to answer and interact with you. Thank you so much.
Thank you, sir.